right, so 3.10 is determining a chemical formula from experimental data. This is kind of a long section. It'll probably take more than one video to get through all 310, by the way. If you are confused, and this is difficult, I'm saying this is probably one of the hardest sections in the whole chapter here. Your book does a great job going through this. If you need to read your book, do it. If you really want to try to figure this out, I'll help you the best I can, but sometimes maybe just sitting down with a book will be the best. If you need to study in detail, refer to your book, especially the last part of this section, okay? The first part, most people do really, really well with because they can go along with the VV-MOL-V wrap, okay? VV-MOL-V can make a guest appearance next time we meet, and hopefully this will make a little more sense. But I can help you out. I can try to be as cool as VV-MOL-V and just give you the voice recording of the rap. I have memorized it from VV-MOL-V. It goes something like this. Something like this rap will define empirical formula, but that don't rhyme. The smallest whole number ratio. Together, let's do it. Come on, let's go. Oh, I need a beat. Can you hear that? Percent to grams, grams to mole, divide by smalls to make the whole. Let's try it again. Percent to grams, grams to mole, divide by smalls to make the whole. There you go. So VV-MOL-V will make a guest appearance, don't you worry, okay? But that's the best I can do right now. So if the data is already given in grams, then you've already got grams. You don't have to do the percent to grams, okay? If you divide by the smallest and the whole number is still a decimal number, you may have to multiply it by some factor to get a whole number, okay? So the VV-MOL-V wrap may not be complete, especially with this step missing. So how does this work? Let's check this out. Let's go to problem number 21. So what does it say? A compound containing nitrogen and oxygen is decomposed in a laboratory and produces 24.5 grams of nitrogen and 70.0 grams of oxygen. Calculate the empirical formula. Again, what is an empirical formula? It is the smallest whole number ratio of a compound. Let's say H2O, the smallest whole number ratio is 2 to 1, so that is the empirical formula. But if you have something like N2H4, that is not an empirical formula. N2H4 would be N1H2 is its empirical formula. So it's the smallest whole number ratio. That's what they're asking you for here, okay? So what's the first thing? Percent to grams. Did they give us percent? No, they gave us grams. So we can skip that step. So now we got to do grams to moles, all right? So, oh no. Here we go. Grams. Well, what am I thinking? Okay, periodic table, you're right. And so what goes on the bottom, everyone? Grams of nitrogen. What goes on top? Moles of nitrogen. And what do you get? You get 1.75. You can calculate that if you want. Okay. So let's see here. I got grams to moles. Divide by, I'm not done yet. I can't divide by smalls. I got to do the same thing with oxygen. Okay. So I have 70 grams of oxygen. Grams, periodic table, what goes on the bottom? Oxygen. All right. And then when I divide it, I get 4.370 moles of oxygen. So now I have my moles. What do I do next? Divide by the smallest. What's your smallest number here? I think it's 1.75. So I got to divide by 1.75. Divide by 1.75. And what's 1.75 divided by 1.75? I get 1. And when I take 4.375 divided by 1.5, I get, or 1.75, I get 2.5. So what's wrong with this? Did I get a whole number? No, I got 2.5. So what can I multiply 2.5 by to get a whole number? 2. So I have to multiply this by 2. And so this is, oopsie, sorry about that. So this is a 2, whoops, and this is a, well, yep, 5. And what does this do for me? It gives me an empirical formula of N2O5. Is this the smallest whole number ratio? Yes, it is. So that's an empirical formula. So the next problem is it has carbon, hydrogen, and oxygen. Calculate the empirical formula. Why don't you pause this and see how you do? I'm serious. Actually pause this, go through the same steps as the VV-MOL-V wrap does, and see what you get, okay? All right, so here I already have grams to mole. I have quite a few moles of carbon, hydrogen, and oxygen. I divided by the smallest number, which is 13.7, and I got a 121, so this is my empirical formula. Hey folks, if you ever get a 1, you can probably leave off the subscripts, but I wanted to show you that. Hopefully that worked out well for you. So look at problem number 23. What's different about problem number 23? They gave it to you in terms of percent. Well, folks, go back and recall what does percent mean? It means per 100. So if I assumed my aspirin, I had a 100-gram sample of aspirin, how many grams of carbon do I have? 60. How many grams of hydrogen do I have? 4.48. How many grams of oxygen do I have? 35.52. So would you agree that this empirical formula might be an intensive property? What does that mean? Does it depend on the size of the sample? No, it does not. So if I had a 100-gram sample, would I have the same chemical composition if I had a 50-gram sample? Yes, I would. So make your life easy. Don't make it more difficult. Make it easier. If you assume you have 100 grams, then your percent is your grams. So percent to grams, you got 60 grams of carbon. You have 4.48 grams of hydrogen. You have 35.52 grams of oxygen. Go ahead and complete the same problem again. Pause this, take a few minutes out, and actually do this. Practice will help you here, okay? So, I mean it. Pause, work on the problem, come back. So this is what I did, and the trickiest part might be, what do I do with a 2.25? Did you know you had to multiply it by 4 to get a whole number? And this is what you got. And believe it or not, that if you Google right now, what is the chemical formula of aspirin, you will get this. By the way, it's acetylsalicylic acid. If you want to spell that out, go for it. But this is the true empirical formula of aspirin. Okay, so problem number 24. Go ahead and work out ibuprofen, and it's the same exact process. Let's see how you do. Hopefully you got this. You probably got 6.5 moles of carbon, so you had to multiply that by 2, so you got C13H18O2. Okay, so that's the empirical formula. The very important process is, what if I want to know the molecular formula? I have to give you one more piece of information. Okay, let's go to your next page. So this right here is the formula that you're going to have to use. So it says the molecular formula is equal to the empirical formula times n. What do I mean by that? That if I were to multiply the subscripts by 2, then I get the molecular formula. So the molecular formula might be an empirical formula, or it might be a multiple of the empirical formula. So how are you going to figure it out? You will be given the actual molar mass of the true formula. So I'll give you a number. This is the molar mass of the molecular formula. So it says use the same steps as above, but when you are done, you're going to divide the actual molar mass, the one that I'm going to give you, by the empirical formula molar mass, and that will give you this n. That will give you what like this 2 is. This is going to be, it has to be a whole number. It must be a whole number. If it's not, you made a boo-boo, okay? And then multiply these subscripts. So let's see what I'm talking about. So for example, the molar mass of C2H6, by the way, this ethane, is equal to the molar mass of its empirical formula times some number. Is that true? Well, yeah. What's the molar mass of C2H6? Periodic table. All right, it's 30.08. It's equal to 15.04 times 2. So that does work out. So if I gave you this, you found this, then solve for n, and you'll say, what's 30.08 divided by 15.04? It's 2, and that's what you'll have to multiply your subscripts by. Okay, so it's one more step than what we've been doing. Okay. So it says butane dione. It's a double ketone, by the way. The main component for the smell and taste of butter and cheese contains the elements carbon, hydrogen, and oxygen. The empirical formula of butadiene is C2H3O. I'm giving you the empirical formula. I am giving you its molar mass. So what is the actual molecular formula? This is an empirical. It doesn't have to be the molecular, okay? This is the smallest whole number ratio of the carbon, hydrogens, and oxygens, okay? So this is what I did. Molar mass of the butadiene is equal to the molar mass of the empirical formula of the butadiene times some number x. So now plug in these values. I give you 86.90. Where did the 43.05 come from? That's 2 times 12.01 plus 3 times 1.01 plus 16. If you do that, you get 43.05. So then divide, I think you do anyway, divide both numbers by x and you're going to get 2. So if x is 2, what are you going to do? You're going to multiply each of these. So 2 times 2 is 4. 3 times 2 is 6. 1 times 2 is 2. And that will be your molecular formula. All right. Now, most problems are going to start off a little bit more difficult. I'm not going to give you the empirical formula. I'll give you something else. So if I give you these percents, can you come up with its molecular formula? Yes, you can. What's the first step? Percent to grams, grams to mole, divide by smalls to find the whole. That's going to give you your empirical formula. Once you have your empirical formula, then go ahead and do this step and you'll find your molecular formula. So I'll do number 26 with you. So what are we going to do here? All right, so what would VV-MolV tell you to do first? Percent to grams, right? Percent to grams. Percent to grams. Okay. Now what? Grams to, whoops, not that. Grams to mole. All right. So what goes on the bottom? Molar mass. What goes on the bottom? Molar mass. What goes on the bottom? Molar mass. Go ahead and divide this out. Pause this, do your math, make sure you get what I get, okay? So pause this. All right, so I got this many moles, oops, wrong one. This many moles of carbon, that many moles of hydrogen, and this many moles, I forgot my equal sign, of nitrogen. Now what? What does VV-MolV tell you to do? Divide by smallest. Well, what's my smallest number here? Well, it's pretty much 3.33, 3.33, 3.33. And what is the first one? You're going to divide that and you get 1. What's this one? You get 4. And what's this one? You get 1. Okay, so what's my empirical formula? C1, H4, and 1. Okay. I'm not done yet. I need a molecular formula. All right, so what am I going to do here? What is that equation I taught you? The molar mass of the molecular formula is equal to the molar mass of the empirical formula times some number x. Well, I gave this to you, didn't I? Here, scroll back up. Didn't I give you that? Here it is. That is the whole molar mass, isn't it? All right, so what is the molar mass of my empirical formula? So folks, what is 12 plus 4, well, 12.01 plus 4.04 plus 14.01? What do you get? 30.06. Would you agree that x equals 2 here? Hopefully you do. So now what? What is the actual molecular formula? Multiply, let me scroll it back up a little bit. Multiply this by 2, so you get C2. H by 2, so you get H8. N by 2, you get N2. And there you go. That's your molecular formula. So I know it's a lot of steps. I get this, but it's not all that bad, is it? Okay, let's see what's going on the next page. All right, so the combustion analysis is a little bit more complicated, so I'm going to make that my part 2. And so I'll just leave you with this. Don't wait to be great. See you next time. Bye-bye.